Okay, so overall, this is a fun topic and something very simple. I just want to show you some with some hand coding, etc. Let's see how does it go. Feel free to interact. So I will be talking some part. I will be using the slides, and something is written in the slide. I will be using some part of the slide into writing things in the code. So this part here, where I'm typing now, so this part will be something that where I will be coding. To run the code, I'll be using this terminal, and this is the slide, which I will present and keep coming back and forth. Okay. So the first thing is I wanted to say how to reproduce this video. So you can see some video here. Let's see. What do you think about this video? What is this, or why is it important? So in the next slide, I was asking, you can go to this link, www.menti.com, use this code. I'm not sure what question will ask, but you can try. But you can unmute yourself and say me or write in the chat that why will someone want to reproduce this video? What do you think? Why is this important in general? Anyone? You can unmute yourself and just tell me. Nothing, you can't be wrong, it's fine. Just trying to make this interactive.
I think it gives a feel about any physical process which we are studying. So
Right.
I didn't get your question exactly. Are you talking about uh, the sense of presentations, or to get some idea of any physical to study particular physical process? So the question I didn't
No,
get.
it's not that deep question. I just asked that why is, something very loosely. I just asked that why is this?
Okay, then I
Why
think
this kind of things can happen or
right.
things
I
like.
think then something which we can. I mean to say images and plot and kind of videos, animations will help us to interact with the audience very effectively or efficiently to convey our proper message. So maybe that point of view it could be helpful.
Sure. Okay. So, so typically, that's okay, right? So here, what I have shown is something. Imagine something like charged balls. So somewhere, these are actually in this simulation. These are just some point particles, not even balls. So everybody is interacting with everyone with something like a Coulombic repulsion or something. So everybody has the suppose the negatively charged, something like electrons, but these are classical, so not exactly quantum particles. So somewhat point particles with some charge, something like a hypothetical point particle with some classical charge, and everybody is repelling every other particle via suppose some interaction. So you can change the interaction potential from Coulomb to say any other Leonard Jones or anything else of your choice. But here essentially what I'm showing is individually each of the particles are interacting with the pair potential. You can change it from the pair potential to an individual collision or any other thing, maybe something like a neutral collisions or maybe magnetized collisions, anything. Anyway, this is just a very simple representation. The idea is the idea in this talk that I'm trying to impart is, can we write a very small Python code in suppose 1 hour or so that we can reproduce this movie? This can appear in many perspectives. You can think of it as something like air molecules colliding with each other. If it is air molecules, they will be neutral, so it will be only collisions. If it is, suppose, something like somewhat bigger, some colloidal particles, small particles colloidal, then it will be with some prescribed initial interaction potential or so. For your own purpose, it will change, but the fundamental way of implementing and all these steps will be the same. So this has, in general, this has many applications it can have. You can cast your answer here. Right. So assuming that you appreciate the importance of the movie, that you want to, suppose you want to reproduce the movie. How will you, as a first step, imagine you, when I was, suppose, in the college or masters, how will I reproduce this thing if I'm a college student or maybe university student? So I don't know anything about the ODE solvers, and I have just entered into the, I just know about something called this Newton's, Taylor's correction or something. So in the previous thing, if we go back, oh, no. Here, I said that the individual particles or individual of this, every blob is interacting with every other particle, right? So let me imagine that I have n particles. For this particular movie, this is there is n equal to 1000 because there are 1000 particles. And they don't have a structure. So initially, let us assume this is somewhat like a point particle. So each of these 1000 particles are interacting with rest of the 999 particles. If you choose one of this 1000, there are 999 left. And so I know the position of the particle, which is x, y, and z, because I have three space dimensions, which you can see here, x, y, y, and z. And since the particles are moving in all the three directions, if they have a velocity, which is v, it should have three components, vx, vy, and vz. And we know the basic equation of Newton's equation, right? That force equal to mass times acceleration. So we can essentially write it as, so we can have essentially three accelerations, which is suppose ax, ay, and az. So every particle, to describe every particle, we will need 6 quantities, x, y, z, vx, vy, vz. And to get the updated position and updated velocity, we will need the information of ax, ay, and az. This is what is just the simplest Newton's law. So we are actually not doing anything beyond Newton's law. No hi-fi physics, no general relativity, no quantum mechanics. Everything, the life is classical, simple Newton's law. Let's try to look at this piece of code. So I guess you are already familiar with the for loops in the Python. So we can, first forget about this heavy chunk. Just let's look at this part. Let's try to annotate. Can I note it on this? Yes. So what does this part say? Probably you have already learned this. So this says essentially V equal to, so this is something like a V, suppose t plus 1 equal to Vt plus A into dt. Sorry, I crossed that. And this also says position, suppose R, if I call it R, t plus 1 equal to, my handwriting has come bad, R t plus V into dt. These are vectors. So if I give you a for example, if I give you a position of one particle, I know, suppose in one dimension, I know the position as suppose x at t equal to 0, and I know the velocity of a particle v at t equal to 0. So this information I have given you, and so this is given. This is given, and I want to know what will be the position of the particle at a later time. Now, there are several caveats. What do I mean by time here? Essentially, you can first of all, you can think of it, think it as in the form of a simple map. There is no no time iteration, but it's easy for me. If I give you the acceleration, so plus the information of acceleration, suppose a0, then you can use this formula and you can find the velocity and position at a later time. You won't be able to get acceleration at a later time. You have to get the information of acceleration from some other things, which I have done here, essentially. So the first step, given all the position, velocity, and acceleration at initial time, the first step will be to calculate the velocity at a later time. Okay. So here you can see Vx. I have kept Vx equal to Vx plus Ax. So if I discretize it into 3 different components, x, y, and z, so this will give you Vx. So this is the x dimension. Imagine I have done this for 2D. Imagine I do it in 3D, then I will add one more dimension, Vzi equal to Vzi plus Azi into dt, and the stuff in the z direction. Okay, by the way, if you feel that I'm going too slow, just let me know. I can then gear up. It will help me. Okay, and here I told that I'm using the pair potential where, so this is true for one single particle. Note that at t equal to 0, if I somehow externally impose an information of acceleration here, this is fine, but at t equal to 1, at the next time step, I won't know where from the information about acceleration. So I'll have to figure out what is the value of acceleration at t equal to 1. Okay. And there are different ways of measuring the value of acceleration at t equal to 1. One way, I mean, depending on what is the potential, if I am in this sort of premises of this problem, then one way is to calculate the position, calculate the value of acceleration from this difference of position. And if there can be different ways. For example, this is one way. Molecular dynamics kind of algorithm, this is one way. There are multiple other ways to measure the acceleration for different particles. Okay, so here, how did I calculate the acceleration? Initially, I said Ax, Ay as 0 for every particle. So if I have multiple particles, imagine I have 2 particles, this particle 1 and this particle 2. And if they are interacting, so this has a coordinate, suppose x1, v1. So now this one is not time, this one is the particle index. So if I give someone the initial value of x1, v1, and a1 for particle 1, and x2, v2, and a2, this is the particle index 2, I can calculate the information of, suppose this is at t equal to 0, or t equal to t, suppose. I can calculate the information at x1 for particle, this is t plus 1, v of 1, this is t plus 1. I won't know what is the value of a. Similarly, I can calculate this for x2, which is t plus 1, v2, t plus 1. And now, if it is only position dependent, for example, here, the expression for acceleration does not contain any information about velocity. If it is not a velocity dependent potential, I mean potential because you take the derivative and you get the force. So as long as it is not a velocity dependent potential, you can calculate it this way. If it is a velocity dependent potential, there are different other ways. But given that it is only pair potential, it is acting only between two individual particles, and each of the pairs, you have to run it on a nested for loop. So this is one for loop for this suppose this 1th particle, and this is another for loop. Yeah, Sukhdev is trying to tell something. Okay. This is for ith particle, and this j is for if I sit on the first particle, I'm running a loop on 2, 3, 4, and all these other particles. So that's why I say if I not equal to j, this is important, because otherwise I minus I will be 0, and then since there is a r, this will be 0, and by divided by 0 will cause trouble, which we are not using the self potential, so there is no issue.
Excuse me, sir.
Yeah, sure.
Sir, here we are using the r cap by r square, like for the force.
Right. R cube. So
R,
if you have
r cap
something like
by
1 over r square as a force, then it will be, in the vector notation, this is somewhat like r vector by r cube, right?
Yes, yes, yes.
So this is r cap.
Yeah, we are taking the components, x and y components.
Right, that's it, exactly. And when I say plus equal to, this means essentially keep
Xi
adding.
equal to x plus 1.
Right, good, right. Okay, so this is what we already know. And as I said, this is wrong because we know that there is a lot of error that creeps into it. So let's first try to write this, and let's see. Good. Okay, so let's first keep this written. I have an editor, and I'm just writing this stuff for I in range n. You can choose your favorite editor. It's fine. Oh, sorry, my Fortran habit. AYI equal to 0.0 for j in range. If I not equal to j, x difference equal to bracket xi minus x of j, y difference equal to yi minus y of j, r equal to math square root of x diff star x diff y diff star y diff. Better to write r star r instead of r cube. So essentially, this is the fundamental thing. So we have got this written. So we already know that this is wrong. Wrong means if I keep updating it. So I guess now you have understood that if I keep updating this thing, there will be a truncation error, right? Because this is the Taylor series error. That if I am on a so this just takes the linear correction for any derivative. So it will depend on the how small the dt I am taking. It will depend on the smallness of the difference in time, and this will introduce some sort of a very tiny amount of error in every time step for every particle. And so essentially, if I need to know the position of all the particles at a something like a little later time, the amount of error that will creep in, that will be very much, and very soon my calculations will be all wrong. So what can we do? Well, so I have already said that what we will lack, the conservation properties for the previous scheme that I have just showed, the conservation properties are not very good. What do we need? Why do you need high accuracy? So this is something that you can ask. So I just so this is a famous. Many people just quote it like this: with your accuracy of algorithm, if I fire a rocket from here, can you land on the moon? Because if there is a very small, tiny error in your calculation, you'll miss the moon, right? Or maybe now Mars. This basically says that why do we need higher order accurate algorithms? Or, as I said, avoid collisions with a meteor while driving a spaceship to Mars. Yeah, if we need higher order accuracy, you can. So there are multiple ways. One is something called leapfrog algorithm or Verlet algorithm, and you can compare the accuracy with RK3. There are very nice references. There are very nice books by Duran or Moin. You can read how they're different. You can ask me why did I say RK3 not RK4? So there are a lot of things behind this. But anyway, overall, this kind of the leapfrog or validator, these are kind of some split algorithms on time. So these algorithms is known to have much better conservation properties, which are important for our purpose. We need to have very high order conservation properties. RK3 and RK4, they are important for some other type of problems, not especially the extension of this leapfrog or Verlet algorithms, which are called the Boris algorithm. They are better for problems where I said the velocity dependent cases. For example, what can be an example of a velocity dependent case? Something like a medium with a drag. Right? You know the drag is typically scales with the velocity. Or suppose a charged particle in a magnetic field. So if you have a magnetic field, the force on this will be dependent not only its position but also its velocity, right? Because it will have a tangential motion around its. The velocity will be basically tangential to its path described. So for all these sort of cases, if you use some extension of this leapfrog or Verlet algorithm, this will have much better conservation properties than RK3 or RK4. So in general, these are important. I'm not sure. Can you guys write in the chat or maybe unmute yourself and tell how many of you already know about the conservation properties of leapfrog or Verlet algorithm? And if there is a sizable number, then I can simply go over that very quickly and then go into the next stuff. Okay, you can also write me in the Menti this stuff that if you have heard of it or not. Let's by that time go into the somewhat like this velocity Verlet. So mainly I'm using the velocity Verlet, not the leapfrog. There's a subtle, very tiny difference. The difference is that in Verlet algorithm or Stromer algorithm, whatever, you measure the value of you measure the position and velocity at the end at the same time step, unless leapfrog. Leapfrog is something which is considered to be symplectic. I mean, by symplectic, I don't go for the jargon. By symplectic, I mean somewhat like for this kind of problem, it's just something like energy conserving. It's actually much bigger thing. It has other momentum and other conservation properties as well, if an algorithm is symplectic. So for the motion of the planets, Kepler first showed things, and it is known actually from that Newton himself knew the leapfrog algorithm pretty well. And he's considered to be one of the first pioneer of this idea. This is how he calculated the stuffs, not something like just like the Taylor kind of truncation that I showed you in the last slide. So here, this is something Newton knew that this will cause trouble. So he used this kind of algorithms. Many years later, people again rediscovered this stuff, and yeah. Okay, so what is different here? You can see whatever is different, I have just written it, highlighted it like this. So in the earlier slide, we had this part is all the same. By the way, can someone unmute yourself? Okay, so there's something in the chat. Okay, not heard and not heard of it. Okay. So let's see. So this part is the same as previous, as I showed earlier. There is no difference. Only thing is, earlier, instead of ux, this was vx, and this was vy. And this dt by 2 factor, this was not here. And here I had this part was not here, so earlier. So now what I'm doing, only this part is extra. What I'm having here, this for I, so essentially, as I said, initially, suppose I know all the position, velocity, and acceleration. So given all the accelerations, I calculate the half velocity. So this is essentially, this is not half velocity, this is velocity at half time, because this is something like this by 2. So velocity at half time. So you calculate the velocity u at the half time, ux, and similarly this thing at the half time. Using the information of this half time, velocity at half time here, you calculate the position at a full time. So this xy, this is calculated at the full time. So remember earlier, this xy, this was here. Now I don't calculate the xy from the full velocity like here. Rather, I calculate the position from the half velocity at full time. Position at full time using the half velocities. This is the half velocity, and then I recalculate the acceleration just the same way I did earlier. I recalculate the acceleration, and then using this new accelerations here, I again propagate it by half time. All these u's, whatever I have calculated here, I put it here. I propagate the u's by half time. So from the previous time step, I already calculated the velocity at half time. If I propagate it by half more time, it will be the velocity at the full time. Okay. So this is the velocity. So essentially, at the end of this whole stuff, all the information I have is Vx. This is at exactly t plus 1. X or y, forget about this. So let's take the velocity vector. And this position, this xy, so this, if I call it as r, so this also I get at t plus 1. Okay. Because these are calculated with dt. So this is much more accurate. And essentially, effectively, these algorithms can be very easily extended for velocity dependent potential. For example, as I said, in presence of magnetic field, or suppose in presence of drags, or any other thing. It can be very easily extended. In addition, if you have something like interparticle physical collisions, they can also be very easily modeled here. So this is somewhat like a very flexible algorithm that you can very easily extend, and very accurate, because it conserves a lot of properties with very minimalistic change with your time pusher. You don't have to go like RK3 or RK4 where you keep calculating the right. Which formula, there is a question, which formula we are using to calculate the accelerations AX and AYs, right? So this depends on your problem. For here, I am taking some model thing which is basically Coulomb. Okay, so I guess it's not, is it not clear? So if I know the potential as 1 over r, this is u of r equal to this, then the basically, if this is the potential, then the force will be somewhat like minus 1 over r square, which is essentially r capped by this, the question that was asked. So this you can write as minus r vector by r cubed. And now if you break it down to different components, then it will have essentially, so this is the force vector. Force will be minus of u, so minus cancels this stuff. So force of x will be, or acceleration, suppose ax will be the the component of this R, which is essentially X, or this R is basically Ri minus Rj. So this is something like its difference, which I've said here, by this Ri minus Rj whole cube. So is that clear? Somebody has asked this in the chat. Is it
So,
clear?
are
Yeah,
we
you can
taking
unmute. Sure, please.
mass and charge as unit mass and unit charge?
Oh, sure. Yes. So life is nice here. Suppose I renormalize everything. I don't know how, but you can put your normalizations at any time there. You can have some mass difference of mass, difference of charges, etc. So for now, forget about everything. For now, I'm suppose staying in an ideal universe where I have all the particles with the same mass and all the particles with the same charge. I don't know how, but imagine this is the thing. And if I have two particles like this, if I know its position and velocity, what is R? Essentially, R is root over x1. So this is 1 and this is 2. x1 minus x2 whole square plus y1 minus y2 whole square. You can see. So x1 minus x2, I call it something like x difference square plus y1 minus y2 is y difference square, I thought. So this is the R.
Yes, sir. It is clear. And I have one more doubt.
Yeah, sure, please.
Sir, the half time, velocity at half time, I'm not understanding why we are calculating the velocity at half time.
Right. So this is something, if you calculate the velocity at full time and the position at full time, you remember there is a truncation error. There is a if you think of a Taylor series, the first term of the Taylor series, suppose you have some function, you're expanding it around or x0, suppose, then if the fx at f of x plus h is equal to fx plus h times derivative at that point by some factor, 2 factorial or something. And then there are some higher order corrections, right, in the Taylor series?
Yes, sir.
So those higher order corrections we have neglected. And we have said, imagine all those corrections as 0. So locally, so there can be a surface can have much higher curvature, but somehow I said that imagine at that point, the surface is only parabolic, I mean, x square and something like that, and locally flat. And then that is the assumption that gives us the Taylor formula, right? The formula for approximating the velocity and acceleration. Okay, that's the thing that I showed in the first slide.
Yes,
No, that is not true. That's not true. We are ignoring the higher order corrections. But if you want to incorporate the higher order corrections, it's going to give you, if it's going to need, for example, if you need to calculate the position, it will not only require velocity, it will require acceleration too, if you need to keep the higher order corrections. Similarly, for velocity, you'll need something more and you don't have the information about it. Right? So you have to do something which is smart, and you can afford truncating the series in a meaningful way so that you calculate more accurately. And essentially, so how does all these other algorithms work? RK3 or RK4, they just simply calculate it at a different. So for example, RK3 or RK2, suppose it's not symplectic, but still you divide it and then you measure the slope at a half or maybe 1/3 point, and then you just predict the slope and use that predicted slope and with some coefficients and things like that, right? So these things are not something called the split time algorithm. Split time algorithms, this is kind of a strong split. So this kind of split time algorithms are little bit difficult to tackle initially, but they are beneficial in a long run. So this is why typically people use this. Okay, so let's try to implement this. How are they different? For I in range of n u of x of I equal to vx I. These spaces have no meaning. U by of I equal to Vy of I plus Ay of. Oh, sorry, I made a mistake. And then these two, x. These were ux at the half time, u, and these are now u. This is by 2. Okay. This is better, but still wrong. Why? What went bad in the last slide? You can see that there is no boundary, right? So the particles will just keep going away and away and away from each other. I already answered. I should have kept it hidden. Why? Because the potential is pure Coulomb, right? So if you have only repulsive potential and there is no boundary, the particles will keep, it will have some sort of pressure, right? So they'll keep going away to infinity. We need to either hold it or do something, some sort of boundary condition. So how do we, finally this looks useful. So this is essentially the same thing that I used earlier, except that this two line is added and this part is added. Okay. So these are called the periodic boundary condition, but you can implement whatever boundary condition that you want to know. By the way, answering your previous question, somebody asked, why this potential? There is no need of taking this potential. You can take any potential that you want, including velocity dependent potential, including collisions or anything. So this is something that just one example I'm showing, probably the easiest example of this world I'm showing to you. This is just something I'm doing, choosing the easiest example so that I can finish it in 1 or 2 hours. That's it. Nothing great about it. For your own problem, you'll have to use your own potential and whatever. Maybe something like 1 over r to the power 12 minus 1 over r to the power 6 or minus of that. Something like Debye-Huckel or anything, depending on in which domain of physics you are working. Okay, so how does this work? So this essentially is nothing. If a particle, you can sit and think, so x is equal to x, so this is fine. Minus of, if you do this, if you initialize a particle into a box of length, suppose Lx and Ly, and what do you do? If the new position is going, suppose, let's note it. If I have the particles initialized in a box like this, so these are all the particles initially. And now imagine at the next time step here, the position, here I'm measuring the position of the particles. If the particle is taking a new position here, this particle, suppose, is taking a new position here, and that's not allowed, right? So what we are calling that, so imagine you have a periodic boundary. So essentially, if something is going out from here, it is coming in from this way. There are multiple explanations of what is a periodic boundary, etc. But anyway, So this position will be this much distance, it will travel in this direction. It will be somewhere here. Okay? And since the particle's new position is here, and since essentially it is a fully periodic boundary, this particle coulombically should be able to see this particle, even though physically they are at this distance. So essentially you are thinking this as a much bigger part of a much bigger system like this. So when the particle moves here, something was here that has come here. So that is the reason you just introduced this two corrections in the measurement of the acceleration. It's initially it's a little bit fuzzy, but if you actually sit and look, suppose if xi is less than lx, then this part will give you 0. Int means the integer part of this. So int of this is 0. 0 times 2lx is 0, so x will be x, right? And now if x is greater than lx, something lx plus something, then int of that will give you 1. So this will be something like x minus 2lx. So if this is the new position, minus 2lx will flip you here. Similarly for the acceleration. So this is just this much. If you do this, then what will happen? At least the particles will not go out. But it's not necessary that you will always have periodic boundary conditions. You can have reflecting boundary conditions, or you can have any other thing, depending on your problem. For now, I'm not going for any other difficult stuff, and just trying to keep this as simple. Just to show you some examples. Minus of int of something x of I by x. By the way, if you feel that you already know this, let me know, then I can gear up and go to the next stuff. This y, this is y, this is y. Yeah, I need these brackets. This is minus round of yi minus y. Should have made this copyable. Right, so that's it. So we have this stuff now here. Okay. Let's go to the next. Are we done? Right, so this is something that takes you initially the particles with some position and velocity, right? So all I need to do now is, and we are good to go. So all I need to do is to put the whole stuff into a time loop, because now you can see that given an initial, so as I said, an initial is the particles with some position and velocity. So if I suppose give some initial random position and random velocity to the particles, I can, so let's do that. So suppose for t in range something, suppose len of time. And don't worry, you don't have to copy these things. I will just share, and I already have a web page, so I will just share the link. So it's nothing great. In case you are copying, you don't have to copy this. Okay. And all I need to do finally, I don't need anything. So that's it. I have to, so what will it do? Initially, suppose I already, as I said, initially, I already know the position, velocity, and acceleration of the particle somewhere here in this space. And then when it enters into the time loop, it knows the acceleration at the previous time. It calculates the half velocity using the previous time's full velocity. And it using this half velocity, it calculates the position. And then using it just checks whether it is in the periodic boundary or not, and then it recalculates the acceleration at this new time. So some simple algorithm, you can use your own algorithm here to measure the forces on the particles, and then it recalculates the velocity at the full time. So this is at the full time, okay? And then it goes, and then again comes at a later time. In the later time, these velocities Vx and Vy come here in this here. And then this acceleration, the information here, this comes here. It calculates again the half velocity and keeps moving in the loop. Okay. So what do we need? We need to initialize the all the particles, right? So for initialize all the particles, you can do this. So fine. Suppose I do something which is the simplest, random. And so this is generate a random number between 0 and 1, right? And what I need is I need to sprinkle the initial position of the particles within a box of, suppose, something which is going from minus Lx to plus Lx. So it will be 2.0 star Lx minus Lx. Initial x position, so I will need y and z also. Y, and let's see, z, and I will need initial velocities, some random velocity, suppose. So this will be somewhat like, suppose Vx, this is something which is suppose Vx max minus 2, because initially the particles will not have any negative velocity. So I have to.
Sir, one small thing.
Yes, sure, please.
In the part of the code that we have already written, that there we have considered only the x and the y coordinates, right?
Sorry. Yes. Sorry about that. Yes. Thanks. My bad. Okay. Thank you. So this is something initial. I have given the initial position and initial velocity of the particles, and I will need the initial acceleration also. So how will I calculate the initial acceleration? It's trivial. I will just copy and paste this. So I just copy, commands Control C for you, and then Command V. Right. So given this x and y, I now calculate the ax and ay. So this is at the time t equal to 0. So this is all initial. Let me comment this as something like initial particle distribution. This stuff, and then here I'm entering into the time loop. Okay. So initially I have some position. So something I guess you have done in the Monte Carlo type stuff also. Initial position and velocity, and I calculate the initial accelerations. To start with, they are all 0. But then I calculate finally the initial accelerations depending on the position. If needed, you can add your algorithm here to measure them from velocities. And then I go into the time loop. I have not defined anything this time. I'm going to do that. And then I have using this value of ax and ay. So this is all in the time loop. So this part is in the loop. And I know the information of vx, vy from here. And I know ax, ay from here. I calculate the half velocity, and then I know positions, these random positions here. Using this u, it goes here, and then it calculates a new position, periodic boundary, and then recalculates the acceleration. So using this recalculated acceleration, now I calculate the using these half velocities here, and these recalculated accelerations, I calculate the final velocities. And then I loop into the next time iteration where I have these information of this ax, ay that goes here. It's a little bit condensed thing, so you have to be a little bit careful. And these vx, vy, this goes here to calculate the next half steps ux, ui, and it keeps looping. Okay. And what else do I need? Don't worry, I will share all these things. So you don't have to copy. I also have already written it somewhere. So it's already in my GitHub. So, but you don't have to go there and waste your time. And let's do something because I have to initialize this. NP empty. If n is the number of particles, then y. Then if I have vx, so vx, this is for vy, and I will also have ux and uy, right? ux, ui, and I will have something called ax and ay. Oh, okay. What else do I need? I have to tell that I use something called vx max, vy max. Let's take them. Let's suppose I'm just looking for a toy problem. And I need to say what is Lx equal to suppose 10. I know these things will work, so because I tried it earlier, so don't worry. Max equal, because I use the thing length in time. Okay, I have to initialize time. So I have it written somewhere and I'm just using that. I guess these are obvious for you. I have to put the whole stuff into something called this. And the rest of the stuff will be indented. Right? Do I do this right correctly? Yeah. Finally, I have to just let me copy the stuff and stuff just. So I have already done this and I have written it somewhere. I'm not wasting time. These are the standard stuffs, you know. I need to import the appropriate libraries. Import numpy as NP, import. Did I use math? I don't remember. Random. Okay, let's see if I've done this correctly. Do you guys see anything that I have missed? Yes, I have missed one thing. I did not say this. Random C. So I hope this part is clear. Okay, there's a chat. Instead F, please use R in row 33. Row, is it row 33 now? Or I have changed a lot of things. Instead F, please use R. Oh, I see. I guess this one is in. Yep, you are right. Sorry, my bad. Thank you. Also here, I guess. Yeah. Okay, instead of math, you can also use NP. So that's fine. Thank you, whoever have said. Let's try and see. Python. So this looks, it's running. Right. We need to save the information, right? So here, this is just running and doing something. Let's save the information. So I know this. You can do just np.save text and do something. Right, it's not C, it's XY. Okay. So if it is 2 and dt is 0.01, so it should, yeah, why are you saying participants can now see your screen? I don't know. Anyway, so you can see that it is taking something like 14 seconds. But the initial movie that I have shown you, that was in 3D, right? So how difficult it is to go from 2D to 3D. This is in 3D. This is not generated 2D thing. Our code will not generate now. So let's improve it. Let's change the dimension. Let's play and let's take it to the 3D. Ly equals 10.0. And then VZ. This is the
There will
VZ.
be LZ.
Sorry, somebody.
There
What
will
did
be
I
LZ.
as? Where did I
Line 11.
Line number 11, LZ.
line down? Oh, right. Thank you. I missed it. So as simple as this. Oh. Some stuff just loading. Please bear with me. And let me see how fast I can fix this. Easy. Difference. So you may ask me why I'm suddenly interested about 3D. While I'm changing this, let me allow you guys to think why, if it is so simple, if going from 2D to 3D is so simple, why I'm spending time and not finishing the talk. Any thoughts?
Actually, I think because right now that earlier we were restricted to an area, and now we are considering in a cube. So the number of particles, number of positions we have to keep track of has increased.
Correct. Very right. Then
So that is probably going to make this problem much more computationally intensive, perhaps.
absolutely. Let's see if I'm doing some mistake. Oh, something went correctly without error first time in my life. So how much time does it take? So it took around 20 seconds, right? And anybody have some idea about if I increase the number of particles? Now I'm using something like 100. Suppose I go to 500. How much time will it take? Any crude idea? Any thoughts? I mean, of the order of. Not, you don't have to exactly tell me. I mean, definitely if you were running in on a faster
3
machine.
times.
I have another question. Like right now.
Yeah.
Okay.
Yeah, please. Yeah.
Like, shouldn't we have now 3 indices to deal with?
Correct.
Like earlier we had I and J, so we should now have another K, right?
Correct. Exactly.
Okay, so basically, so So by increasing, so
No, wait a minute. I and J is are the particle indices. So if I have the particles saying sitting
Oh,
here,
oh,
it's
okay,
not
okay,
about something like a fluid calculation.
okay,
You
okay.
probably
Sorry, sorry.
have done.
Yes, yes, I understand.
It's the index of the particles. Okay. So that's why basically going from 2D to 3D was so easy. It's but still it is computationally expensive. So so somebody said 3 times. Okay. And any other thoughts? How much time? How expensive it goes as n increases?
I think it increases as n square, right? So
Right, it increases as n square because of this part for
yes,
I and for j. So yeah, I have this thing I, and for every I am calculating this j for essentially not n square, n into n minus 1, but if n is large, you can take it as n square. So this is pretty expensive. Now, so I have taken 100 and I just ran it for a very small amount of time. Now imagine how much particles do we have in the air in one, what is called Avogadro number, 10 to the power 23 or so. So literally we'll be doomed, right? Okay, let's just try to see how fast this goes. I just changed it from 100 to 500. So if I now have 500 particles, let's see the time. I'm already doomed, right? You can see this progress. Time step 0, 1, 2. I don't know how much time it will take to go up to 2. Somewhat like 5 minutes or. Okay, so we'll have to wait for a very long time. So I was going to, okay, let's go. So this is what we had left. Are we done? Almost, but just put it inside a time loop. We have done that. And initialize the particles with some position and velocity. We have done that. And we are good to go. And now, if I'm increasing the n, then it is taking a long time to run, right? And there are traditional sayings that Python is slow, and a lot of people keep complaining that Python is slow. Something a terrible thing. Of course, one way is to rewrite the code in C or Fortran. If I would have written this in C and Fortran, it would have been much more faster. So, okay, so do we have to again rewrite the whole code in C or Fortran, or is there a cheat sheet? And that's basically the purpose of this talk. Oh, so the simplest thing is you don't really have to worry that much. We have something called this Numba JIT compiler. This JIT is called something like just in time. All you have to do is to add this thing from Numba import JIT, JIT no Python equal to true, and that's what it will solve your problem. How far we are? We are at time step 46, and already we are doing it. Okay, let's try. Let's try Numba. What we have to change? We can't. If you are using Numba, we can't use math. So I have to turn this off. And this, so everything will be as the numpy array. So this, let me go to np dot float 64. This is for everybody. Done. And wherever you used math, so we should not be using this math. We should be using np or numpy. I mean, for the other stuff, I could have used np. earlier, NumPy arrays. Why? You can ask me why, because if I use the math, it is actually faster. So if I would have used this same stuff in p.square, it would have been even slower. So the comparison will not be fair. So okay, done. And I don't need to suppose print this stuff. Yeah, that's it. What else? Random time. Another thing is so this is something that I have written. From NumPy import JIT no Python equal to true. I've done here, the rest of the stuff is there. Oh, it's not just finished. Maybe we'll have to wait a few minutes. I want to compare the speed. Maybe I should have chosen someone smaller. So essentially in the code, I have not done much changes.
Sir, where are we using this time library in the code?
Oh, this is at the end. I'm just print. It's not essential. I'm just using it for the measure how much time it is taking to run the code. Okay, so I'm sure you guys are getting bored because it's unnecessarily taking time, which is important. I want to see whether it is doing things correctly. Okay, by this, while we are waiting for the run to finish, any other questions? Anybody?
I have one question, although I think it would be better to ask after this demonstration. The thing is that, like normally Python uses this CPython compiler to convert the code to a Python bytecode and all, and that is why it takes so much time, right? And
right.
yes, so there are other Python compilers like CoMP-Py. So that also basically uses just-in-time compiler. So,
Yes.
yes. I mean, so does this have any advantage or disadvantage over number?
Yeah, so typically they have shown that this NumPy is faster and more flexible and things like that. So there are not only NumPy, actually there are multiple platforms nowadays that does the same stuff. I mean, not only this JIT stuff. It's just your choice. I'm just showing you one way, but there are multiple other ways, whatever you want to do. That's it. NumPy is a recent stuff they have done. And they claim that it is faster than the other things, more flexible. That's it. I haven't ever used the other stuffs. Do you know if they are this much flexible or they need some more treat?
No, actually, why am I asking this is that NumPy does not support all of the NumPy functions. It obviously does not support SciPy. I think so.
I see.
I see, but PyPy is basically Python, so I suppose PyPy would have better support for like now NumPy functions and even SciPy also. I am not sure. I mean,
you can look at the differences, and
yes.
I once looked at this, and in the NumPy, if you go to the web page, they do a comparison with this NumPy stuff with others, and now everybody will claim they are the best. So you have to take it with a pinch of salt. So it took 469 seconds. Let's go to somewhere here and let's document this. It took how much? 469. 469. Okay, 0.46 or something. Does not matter. Okay, now let's run this with Numba. It took 1 second, right? 1.8375. 1.83. So I guess now some of you will be able to appreciate that this is something useful, right? Okay, let's go back. Almost around the end. So I was here. And then I said, still not fast enough. So if imagine, let's go to a case where it is still not fast enough. Suppose I take time equal to say 15. Or okay, yeah, let's go to time equal to 15. And let's try to run this. How much does it take? So if I'm going to 50 from 2, earlier I was in 2, so it is 25 times. Okay, so this took 15 seconds. So this, and okay, so this is some extra time to initialize, etc. Okay, and now if I'm not happy with the speed, let's try to parallelize this. So the most of the time that it has spent is within this time loop, right? This time loop here. So we have to parallelize this part, but we cannot parallelize it in time. So what we need to do is we can parallelize over the particle numbers. So I said some of the loops. So here are the code that I have written now. And for some of the loops, I can, instead of range, I can write p range. So p is somewhat like a parallel. You add a p here, and similarly for I in p range of n, I'm not parallelizing the inner loop, suppose. You can try and keep checking the accuracy. P range, and the p range here. And all you have to change is comma p range. And you have to say parallel equal to true. It's comma parallel equal to true. I hope. And then let's see how much time does it take. So I have here 4 cores in my machine, but not all the 4 will be working because I'm using a Zoom. So at least one. So I'm effectively running it on 3 cores, and it took 6 seconds. Right? So now you can see the speed up. It's hard to compare the speed in here. If I would have run it for the non-parallel case up to time equal to 50, it would have been multiplied by a factor 25. So I don't know, let's try. 469 into 25, which is 11725. So suppose this is 11725 seconds. Here it took around, how much did it take? 15.88. 15.88, and this took around 6.87. Yeah, so that's it. That's the end of the talk. This shows that if you just use this NumBudget or the other stuffs that Shubhadeep was saying, you just need to make some very small amount of changes in the code, and you can get a huge speed up. And if you're running it in parallel, so okay, I'm not sure how many of you know about this parallel stuff. Okay, is that possible or easy to convert this program in parallel code for better performance? Okay, so I just did it, I guess. Anyway,
So,
I'm not sure. Yeah, please.
so I mean, if our computer has say just 2 cores,
Then you can't. You
yes,
be running on 2, yeah. But typically the laptops and computers, even nowadays, the Raspberry Pi comes with 4 cores. And some old Raspberry Pis have 2 cores, yeah. But yeah, your laptop typically have 4 cores, and if you are running on a cluster or on a workstation, you'll have around 16 cores. If you're running it on a cluster, it can have a core from 40 to 90, 100. I mean, it's the multiple of 2 typically, power of 2 typically. And this is something like OpenMP, so something like shared memory architecture, not something like a distributed memory architecture. So there's some subtle differences. For distributed memory architecture, you have to run it on something called the MPI based schemes. Yes, please. There's a question.
I mean, nowadays these processors, they are advised with something like core and thread. So number of threads that can run on each core is like double the number of cores itself. Like,
yeah, but that's right. So that's something called a hyper-threading.
yes. So because
Essentially, it's not increasing your computational efficiency, but it's increasing your parallelization. If you are using more threads, so I mean, exactly, if you have the hyper-threads, and if you have the so these are helpful on hyper-threads. Yeah, that's right, because this is simultaneously you are using more threads, so this should be helpful. But typically, people do not run this stuff on a laptop, so they run it on clusters. And the old generation clusters, the Cray stuffs, they used to have like 1,000 cores or so, very big. Okay, and I have kept something like a very small animation stuff to see whether whatever I was doing. So let's go back to the previous version. How do I have stuff? Let's see. So I have a Python. Animate. Yeah, now you can see this is a movie of all the particles. This is 500 particles, not up to 50. It is something where I ran it up to only 22, I guess. So because at that time it saved all the data. So I have here all the 500 particles. What does this movie stuff do? You can look at the thing. It's trivial, right? Oh, it is running for 100 particles, the earlier stuff. So it has, it's okay, it's running up to 1. There is basically nothing. I guess people who know Matplotlib will understand this. This is just to check whether the stuffs that I was doing something similar or not. This probably takes you to something like the sort of movie I was showing you earlier. You can ask why is on the black background, because this is run on something else, but forget about it. So this is the sort of stuff I thought would be interesting. And there are some questions. Can you please suggest a book for studying molecular dynamics? Yeah, there are a lot of books actually. There's something called Rappaport, D. Rappaport. You can go there, and I mean, if you just go, I guess there are a lot of examples. How the reflecting boundary conditions work in the case if the particles are confined by a parabolic confining potential. Yeah, so that's something not very difficult. For reflecting boundary, you'll have to be careful that. Let's go. For the reflecting boundary, you'll have to be careful that if it's going somewhat like this. If the particle is here, and in the next step, suppose it's coming here, okay, you have to calculate this distance. and this much will be here. Only this part is the difference. So instead of it will go here, instead of going it this way, it will go this way. So you change you flip the velocity of u, you make it minus of ux, but do not flip the velocity in y. Y equal to u1. So it will be this way. And yeah, and a parabolic confining potential, right? Okay, so for a parabolic confining potential, I mean anything about the dusty plasma, huh? You have to add a small, in this acceleration, you won't have this part for deflecting boundaries. You just have extra minus of x and minus of y, because if it is a potential is parabolic, you will have del of x or y or z. So essentially it will be something like minus of x, minus of y, minus of z. So the acceleration, I guess it will be just minus x diff minus, or somewhat like this. You just take the derivative of the parabolic potential and just add it here at the final step. So that's it. It's simple. I did it, and it's very simple. Yeah. Okay. And so I guess that's all I wanted to do. Somebody was asking something. Did I miss somebody? Okay, then let's go to here. So here I have just created a small, let me just take a copy and then where's the chat. Yes. So I'm just putting the link in the chat. Hopefully. So I just said whatever I have did. You can click anywhere in the image, it'll just start the movie. You can see the stuff, and then of course the codes that I've shown you in live developing. Basically, I was looking at this. So you can now see the codes, exactly the same code, basically. I've kept it here. So this part, this code does not have any Numba. This is the slow one. This is the very slow code. This one is with Numba. So all the difference is you just add this from Numba import JIT, add JIT, no Python equal to true, and change this D type to float 64. And instead of math, you should use NP. And if you're running it on multiple processors, you have to run it on this. Yeah, you just add this P range, and this P range, and add parallel P range, parallel to the true. So I just kept the small stuff that I was using to make the movie. So you can now go there. And there are some funny problems you can look at. If I click here, it will take you to here. So this is something that I did several years ago. Let's go. Let's go at this. So essentially, whatever you have seen now is this somewhat similar to this, exactly the same stuff. Actually, so it's just the same. It's except that the number of particles are more here, so it took some more time to run. It is somewhat like 5,000 or 10,000. So. And here I have something extra, which is a box where there is nothing, and suddenly I remove the wall, and you can see the particles are moving out from here. And they have the reflecting boundary condition, whatever somebody has asked, it's good. If you have this reflecting boundary condition, then as you can see, the particles go out. Okay, let's just try to capture that point. Yeah, here you can see the particles are going out and then coming. By the way, can you see the movie clearly, or is it not properly visible? Can somebody unmute yourself and say that?
It's clear,
Yes,
sir.
clear. Okay, thank you. I'm always doubtful of movies. Okay, so this is some sort of a mixing problem or like some sort of a free expansion problem that we are doing. This is a funny thing, and these things are now you can do, I think, very easily. Right? Or for the mixing problems, this is in 2D instead of 3D. It's even simpler to do. So if you look at this part looks like a solid, this part looks like a liquid, and then there is a barrier which separates the two mediums. And now what happens if I just remove the barrier? But let's see, it's some heat wave or something like that. Yeah, you can see a small heat wave. Yeah, these parts are going. And then you can see the two particles are getting mixed within each other. You can just try and play your own problem and funny stuffs. Okay, so that's all from me today.
Hello, sir.
Yeah, please. Okay, most of you said no. Have you heard of leapfrog or velocity weighted algorithm? Maybe two. One said yes. Okay, so probably I bored you. Well, okay, yes. Somebody was asking something, please.
Sir, can you suggest a book from where I can study a little bit of molecular dynamics?
Yeah, so there's something called Rappaport, D. Rappaport. There's a nice book, and I guess there are a lot of things. Let's go. There's something. One of my friends have made a package, PPDIN, 3D, some sort of plasma particle dynamics Python package. And this visualization that you have seen here, where is it? This one. This is made up of something called this. What is called? ParaView, and you can get the visualizations from here. What happens if I click here? It says it's very easy to install, by the way. You can go to a terminal and just say pip install ppdin. It'll install the whole code. You don't have to do anything. It'll have some sort of input file, and you have to probably modify. How do you go? If you go to the home page, oh yeah, oh, something's broken. But anyway, right. So this is the GitHub page for the code. It's open source, and you can just download and plug and play things. And the even more funny thing. Okay, so about the initial input file. Okay, so the animations can be done from here, and this is the input file. You can choose the number of particles, blah, 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 and you can have some screening, different boundary conditions. For example, somebody is asking reflecting or periodic or any other boundary conditions. They have some sort of, okay, as of now is the periodic. I guess it's not difficult to implement others. And this is for visualizations and etc. You can run it in parallel mode, you can run it in serial mode, you have to say true or false. You can change the boundaries and etc. number of particles, etc. And you can have some initial temperature of the particle. You will take it from somewhere. And the cool thing that I like about it is you can just click on this launch binder. If you do this, it'll open something which is here. And the funny thing is, you won't have to have essentially a laptop to run a full-fledged molecular dynamics or something like this particle dynamics. You can run it from your mobile also, because currently whatever it is doing, it's running on a cloud. So it's exactly the same algorithm that is being run and the same code that I've shown, with some more advanced features, of course. But you don't have to have a computing stuff with you. You can open this link from your mobile browser, from a mobile phone, and it will compile the whole code within the cloud only, and you can then, it's not coming now, once it compiles, you can go to the input file, make changes on the input files, and it will run. Oh, okay, so there must be something broken. But anyway, you can change the input file, you can launch your runs, it will generate the data, and you can simply download the data on your at a later time. Don't close this stuff. Oh, it's already done. Now you can go to this new and go to terminal. And once you get your terminal, you can just open something, whatever your favorite thing is, and then you can ask, suppose, good. Say how to run this, but anyway, you have to do. I guess something is wrong here. I'm not an expert. You can ask him. But overall, the general idea is you can make changes in the input file. You don't have to have a laptop. It will run in the cloud. It will generate the data for you in the cloud, and you can just download the data at a later time and use the data for your own purpose. That's it. So it's some sort of fun. Okay, I guess that's all I had. Anything else that you guys?
Sir,
Yeah. Yeah, Dij?
yes, sir. So as we have coded that program that was maybe for OpenMP type of code. So can we convert that code to MPI? Is that possible?
Sure, but it's not immediately trivial. You have to do some more tinkering with it, because going from OpenMP to MPI is a little bit more technical. But of course, it's possible. Yes, there's something called MP4Pi, so you can use that and you can go for better stuff. Yeah, let's see if I have addressed the questions to study the problem. This is for the first thing. Box jiggling and wiggling of atoms, which can be helpful to understand. Okay, it's fine. Maybe used for demonstrate to spread diseases, right? That's right. That's right. Very true. People use that. Molecular dynamics is highly used for sort of targeted drug delivery and things like that. Not hard regarding the, I guess, the leaf frog. Which formula we are using to calculate the accelerations? I have said this. Yeah, thanks, Ram Suthar Patel. Yeah, it was a bug. Book for molecular dynamics. As I said, Rappaport is a nice book. You can just Google. I guess it's not only one book. There are like thousands of books on molecular dynamics. But one good start can be Rappaport, because it starts from something very basic and slowly develops. The very basic steps I have already said. So yeah, you can now, I guess, if you go to Rappaport's book, you will understand the stuff. Except that there is one non-trivial stuff.
Sir, can you spell the spelling?
Oh, sure. Let me just see. Rappaport. Molecular dynamics. I can just share the link. Art of Molecular Dynamics. Yeah, this book. Okay, so type message here. Yeah.
Yeah, thank you, sir.
You're welcome. Okay. Is that possibly easy to convert the program parallel code for better performance? Yes. We already talked on this. Reflecting boundary, and parabolic confining potential. Yeah. So I guess if you go to the PPDN stuff, you will see there are already the reflecting boundaries are implemented, and all this stuff's are there, including some collision physics and all this stuff. Yeah, good. Any other question or anything you wanna add? You wanna suggest, or you wanna improve? Okay, yes. So one more stuff. Let's go to the presentation. you can now again go to your, so I see that you are able to go to the Menti, right? So yeah, do you learn something new today, or it was just a repetition of what you already knew? If you have not learned, I'm assuming you are sleeping. If you have learned, I'm assuming you are awake. So you can write whether you are sleeping or awake. You can go to menti.com and use this code. It will help me to understand how to improve. Or you can send your feedback to me if there is something to improve in my presentation. And that's it. Any other thing from anyone else? Okay.
Hello.
Okay. Sorry, yes, please, Saravanan, yes.
How to fill particle in Vignas itself? Here we used rectangular coordinates. No?
Right.
How to fill in Vignas itself?
So initially it's not at, so here I haven't showed you how to use a thermostat, but you at initially here we have loaded the particles as a random position and random velocity. You can start with that and then keep something like a Bernstein thermostat or stuffs like that. It just takes out energy from that. And then you automatically will get something called a phase transition that you already know very well. And once you achieve the phase transition, then the particles in 2D automatically will come in a hexagonal Wigner side cell. You don't have to load the particles necessarily in a Wigner
Okay.
cell or anything. It is
Okay.
something that will come out automatically. You load the particles
Automatic.
randomly.
The dynamics it will emerge. Yes.
Right, exactly. If you change the temperature of the particle, if you ask the particles, there is something called a thermostat. If you go to the book by Rappaport, you get the information about thermostat. Use the simplest thermostat. This is called the Bernstein thermostat. If you are using the simplest thermostat, it will show a phase transition. Given that, for example, I haven't okay, I'm going beyond the things since you already know, I guess. You know about the Yukawa potential with kappa and gamma, etc., right?
Yes.
Yeah. So if you choose, suppose kappa equal to 1, gamma equal to somewhere below 170, maybe 150 or anything, you will see a phase transition. You automatically the phase of this weakness size phase will come out. So you don't have to worry about it.
Okay.
If you're using the PPD, you can just take the input conditions as k equal to 1, kappa equal to 1, gamma equal to something, and you'll see that it's, but well, I have to be clear, it's in 2D. Your system is in 2D already, I guess. If you are working in 3D,
Yes.
it will have a different parameter regime. But for others, it's a little bit different. So sorry about that. Any other thing that is related to this talk or anything? Okay, let's stop the recording then.